All right, welcome everyone to this week's CFA Colloquium. It is my great pleasure to introduce you to Catherine Espaillat from Boston University. Catherine received her PhD in 2009 from the University of Michigan, and then she moved here where she was an NSF Astronomy and Astrophysics Fellow, and then a SIGAM Fellow. And since 2013, she's an assistant professor at Boston University. Catherine is an expert in planet formation and circumstellar disks, multi-wavelength observations and radiator transfer modeling, and many other things. More recently, variability, which we will hear today. Catherine is also very involved in the advancement of women and minorities in STEM, and she's the director of the League for Underrepresented Minorities in Astronomy, LUMA. And so if you want to talk to her about that later, she's available. And so yeah, let's hear from Catherine today. Welcome, Catherine.
Thank you. And thank you for the invitation to come back and visit. It's always a pleasure to be back. It's amazing to be around so many smart people and have a full schedule. I really enjoyed my meetings today. This doesn't look right. The resolution doesn't look that great, but hopefully the resolution will get better with the next slide. But speaking of, sorry? It's better here. Oh, okay, because I'm too close. Okay, good, thanks. So I'm going to be talking today about variability in young pre-main sequence stars, T-Tauri stars, and their disks. And protoplanetary disks are very interesting because we use them to get to understand more about planet formation. But something that we tend to forget about is that protoplanetary disks are also accretion disks. And they're some of the closest accretion disks, and they're pretty large, so we can resolve them and study them in detail. And also they're relatively bright, so we can study them relatively easily. And we can utilize these protoplanetary disks to learn more about the fundamentals of accretion, transport processes in these disks, and maybe tap into some fundamental physics that can be applied to other kinds of astrophysical accretion disks. And if accretion isn't your thing, accretion onto these young stars generates a large amount of luminosity, which affects the heating of the disk and the chemistry of the disk, and therefore planet formation. So there's something here for everyone, accretion and planets. So today I'm going to be structuring my talk around these three main questions. So first, what do we know about protoplanetary disks, and particularly variability of these T-Tauri stars? And this is going to serve as an overview, introduction to the field. And then I'm going to move on to what do we learn from multi-wavelength data. And here I'll be talking mostly about some recent data that I've collected, trying to understand accretion and the connection to the disk by looking at multi-wavelength data. And then, of course, wrapping up with what is left to learn. We're left with many more questions than answers. All right, and starting off with, what do we know about the variability of these young systems? So first, an overview of what we think we know about protoplanetary disks so far. So we have these disks that are made up of dust and gas around these young stars. As you go inwards towards the star, the temperature increases, and you reach a temperature in the disk of about 1500 Kelvin, where your dust sublimates. And then we think gas just goes into the innermost disk towards the star until it gets truncated by the stellar magnetic field. And the material from the disk is channeled via the magnetic field lines onto the star, forming this accretion shock. And there's a lot of complex chemistry, of course, that happens in these disks that I'm not going to get into, and a lot of physical transport processes, turbulence in the innermost disk. A lot is going on in these disks. So this is a snapshot of what we think we know about protoplanetary disks. And luckily for us, we can observe protoplanetary disks at many different wavelengths. So starting from outside going in the outermost part of the disk, particularly in the midplane, you can trace that in the submillimeter and the midplane and the millimeter. You can get to, so disks are optically thin at longer wavelengths, so you can trace the dust continuum down to the midplane of these disks. Going inwards in the mid and far infrared, you're starting to trace the uppermost layers of the inner part of the disk, so around 10 AU or so. And going in even closer, so at this point where the dust is truncated in the inner disk where it reaches dust sublimation, this happens at around 0.1 AU, and here we're really looking at, we can really probe this region with near infrared. And the gas that goes inward towards the star within this the truncation of the dust in the disk. That can be observed well in the near infrared. And then this accretion process onto these young stars, it's a very energetic process. It has temperatures of about 10 Kelvin or so, 10,000 Kelvin or so, and emits very strongly as a continuum in the ultraviolet wavelengths. And I'll be focusing today mostly on what we can see in the ultraviolet, the near infrared, particularly focusing on the inner dust rim, and bringing in a little bit of the X-ray. So to start off, so variability in these young disks is very well known. 1945 was the discovery of the first variable T-Tauri stars, and there's no way I can do justice to the amount of work that's been done in the field of variability in the past 70 years. So I'll be focusing mainly on the variability that's much more recent work. But yes, variability in these young stars is very well known, and it's now become a characteristic of these stars. T-Tauri stars are very variable. And with different space facilities, we've been able to really expand our knowledge of variability in these young systems. So this is an example from Spitzer, which probed the mid-infrared. So these are two mid-infrared Spitzer spectra of a young system, UX tau A, and they're different colors. They were taken about a week apart. And before I break that down a little bit, just to tell you that the structure of this disk has a big gap of about 40 AU or so. The inner disk is at the dust sublimation temperature in the disk is what's giving us the emission here in this part of the left part of the IRS spectrum, and the emission from the outer disk is dominating the emission here at the longer ends of the IRS spectrum. So we see this kind of seesaw variability where if you look at the blue spectrum, it's lower at the shorter wavelengths, and then it's higher at the longer wavelengths. And then the behavior reverses, where the red spectrum is higher at the shorter wavelengths, and then it becomes lower at the longer wavelengths. And this was a sample of about 11 T-Tauri stars. And we were able to reproduce the seesaw variability that we see in these objects with our disk models just by changing the height of the inner rim of the disk, and therefore changing the amount of shadowing on the outer disk. So just to break that down, this corresponds to the blue spectrum. So in this case, in our model, this dotted line, we have a short inner wall. And here we're assuming very simplistic vertical walls. Very short inner wall that casts a smaller shadow on the outer disk. So what you get is less emission from the inner wall because it's shorter, so it's reflecting less light. It's thermally emitting less light that it captures from the star, so it's lower. But then the shadow on the outer disk is smaller, so you see more of the emission from the outer disk. So that's why the emission here at the longer wavelengths pops up. And then the reverse is true here to fit the red spectrum with the solid line. We increase the height of this wall at the inner rim of the disk at the dust destruction temperature. So you see more emission at the short end of the IRS spectrum, but then the shadow on the outer wall is bigger. So you see less emission from the outer wall. So the red spectrum goes down. So this is just an example of how Spitzer advanced our understanding of variability in disks, where before we thought just the stars, predominantly just the stars were variable, but also it seems that the disk is variable, and this could be pointing to structural variability in disks. And of course, our models were very simplistic, just moving vertical walls up and down, and there could be many different explanations for what can cause the inner rim to change. So planet-disk interactions, where a planet can warp the innermost disk, or where spiral waves generated by the planet can propagate into the inner disk. Turbulence can also cause small changes in the height of the inner rim of the disk. And you can also have some interaction with the magnetic field. And more recently, there's some very promising work where with HST and SPHERE, people have been able to image and see a shadow moving across the outer disk, which tells us that there is an inclined inner disk that's moving around and casting the shadow that we can actually see now. So it'll be very interesting when JWST finally comes around that we can start to probe, is the seesaw variability that we're seeing due to these inclined inner disks. So that's just one kind of variability that we've seen since 1945 with Spitzer in the mid-infrared pointing to disk structure variability. And then, of course, with Kepler and Corot, we've had amazing length of coverage and cadence in the optical wavelengths. So here are some examples Corot observations taken so this was taken from a larger sample of 500 T-Tauri stars observed over 40 days with a cadence of 8 minutes. And when Cody et al., when they looked at this massive data set, they found about 4 categories into which most of their sample could fit into, which is represented by these 4 different kinds of light curves. So the first class is called bursters, where these little peaks in the optical emission, and stochastic. And both of these have been linked to variable accretion onto the star. So there's some kind of changes in the mass that's accreting onto the stars that leads to these kinds of light curves. They also found quasi-periodic variability in the light curves, which they explain with star spots, either cold spots or hot spots rotating with the star's rotational period. And then there's also these dippers, where there are big dips in the optical, which is most likely due to extinction by circumstellar disk material, and most likely disk warps. So I'll be focusing mostly on bursters because we followed up in detail one object that we think is a burster. And so talking more about accretion variability here. So before I go into accretion variability, first I want to tell you a little bit more detail about accretion. And now I'm zooming into the inner 0.1 AU of the system, where here we have the magnetic field lines, the accretion flow. We think that along this accretion, the magnetic field lines, we get broadening of emission lines. And I'll show you an example of that in a couple of slides. And then once the material impacts the surface, it forms this hot continuum, which emits predominantly in the near ultraviolet. And in order for that scheme to work that I showed you in the previous slide, we need strong magnetic fields in these young T-Tauri stars. And they do indeed, based on observations, we think that they have strong magnetic fields of 1 to 2 kilogauss. And these observations are mostly made utilizing the Zeeman effect in 2 different ways. So one on the left is looking at lines that are sensitive to the Zeeman effect and fitting the lines. And I'll get to that in a second. And on the right here is looking at the polarized circular emission in Stokes V. So here on the left is one object dk tau, looking at different lines that are sensitive to the Zeeman effect. The broken line corresponds to a model with no magnetic field, and the solid lines correspond to a model that have a magnetic field of about 3 kilogauss. Here in black, we have the right circularized polarized emission, and then the left in the gray, and the difference between the two for GQ loop and TW hydra in helium-1. And GQ loop is measured to have the strongest magnetic field of a T-Tauri star of 6 kilogauss, and TW hydra has a 2 kilogauss magnetic field. And utilizing Zeeman Doppler imaging, we get more insight into the geometry of the magnetic fields in these young stars. And this is an example of V2129 Oath, and you can see that things get very, very complicated. On the left here, we have a high-order magnetic field. Here's a dipole magnetic field. And this is a simulation of how it's thought that gas accretes onto the star via the magnetic fields. So this slide is just to demonstrate how complicated the accretion process is in these young systems. And I'm going to be using much more simplistic models, trying to tackle this problem of measuring accurate accretion rates and what can we learn about the accretion process, and hopefully get to this level of detail in a few years. So first, what are the different diagnostics that we use to measure accretion in young stars? So this is BP tau, observations in blue, ranging from the optical to the millimeter. The photosphere is here in magenta. And I want to draw your attention to the photometry, U-band photometry at the shortest wavelengths. That's probing the NUV, the UV excess that I told you about that's due to the accretion onto the star. And you can see this much more clearly if you get HST near ultraviolet data. Well, the data are in gray, and the photosphere is in blue. And the excess here is all due to accretion onto the stellar surface. And I'll break down these lines in a couple of slides, how we model that emission. But first, just to show you that with STIS and UV data, we can get very accurate measurements of the accretion rate. And also something that's very common is looking at H alpha. So there have been studies that have looked at the accretion luminosity from STIS and found correlations with H-alpha. So H-alpha is a much easier thing to get for larger samples, and it's an accurate way of measuring accretion rates. And the average accretion rate in these young stellar systems is about 10 to negative 8 solar masses per year. So how do we go about modeling the accretion rates? So how do we extract accretion rates from the excess that we see in the STIS and UV data? So this is a simplistic model of an accretion column. So we're assuming that the shock is plane parallel. So a very simplistic model. And the idea here is that the shock, half of the emission goes down and heats the photosphere. Half the emission goes up into the pre-shock. This pre-shock processes the emission, sends half of it back down into the heated photosphere, and half of it leaves the system. And here, so the total model here, so again, the gray is the data, the blue is the photosphere, and the red is the total model. And that consists of the heated photosphere in dashed here, and the pre-shock emission, the dotted emission. So when I show you these models again in a few more slides, I'll just be showing the total emission here, but just to explain how we're using the accretion shock models to pull out the accretion luminosities and the accretion rates in these disks. All right, so that was the broad overview of accretion in these young systems. Now I want to move on to what do we learn from multi-wavelength data, and focusing particularly on a recent program that I have going on to try to understand T-Tauri stars, their accretion, and how it's linked to the disk. So first I want to, I just showed you these beautiful Corot data. That's not what this is going to be. So we have a small sample, and the strength is the broadness of the wavelength coverage, which to the best of my knowledge has not been done before for a T-Tauri star. So we have the broadest wavelength coverage for one T-Tauri star, and we have reasonable wavelength coverage for about 5. So much smaller samples, but again, the strength is that the data is multi-wavelength, and it's also either coordinated within 12 hours or strictly simultaneous. You're able to get strictly simultaneous data in some aspects. So the first data set that I want to go into is our HST data set. So with HST, we get UV, optical, and a little bit of near-infrared coverage, but really HST's strength is giving us access to the UV, so the accretion, directly extracting the accretion luminosity onto these stars. And for 5 targets, we got somewhere between 3 to 5 epochs per target. And here I'll be reviewing work that I submitted. So my student, Connor Robinson, spearheaded this effort. We submitted the paper, we got a favorable referee report, and we're hoping to resubmit sometime early next week. And then I'll be telling you about, we got coordinated HST and X-ray data with Swift, Swift and Chandra for 7 targets for 1 to 5 epochs. And I'll go into a little bit more detail about the Chandra data in a bit, but here when I say coordinated, I mean within about 10 hours or so, 10 to 12 hours. So simultaneous X-ray, UV data, and this is a paper that I submitted, and again, the referee report came back favorable. I'll probably resubmit that in a couple of weeks. And I'll be telling you a little bit about that. And then for one target for 8 epochs, we got coordinated HST and infrared data. So and I'll break this down in a bit, for the first 3 epochs, we got ground-based near-infrared spectra with NASA IRTF within about 12 hours again, so half a day. And then for 5 epochs, we got strictly simultaneous infrared data with Spitzer overlapping the HST data. And this is some work that's been, the data with IRTF has been published previously, and then the rest is in some in-prep work that I have that I'll tell you a little bit about. Now, I won't be telling you in detail about some follow-up observations that we did for an interesting object that I'll be focusing mostly today, Giamoreggi, because I haven't had time to go through all of the data. But for one object, Giamoreggi, we got simultaneous, so strictly simultaneous Chandra, HST, Spitzer data, ALMA data for a week, spanning between the observations. The observations were roughly a week apart. VLA data within about a couple hours for 3 of the epochs, and then ground-based optical spectroscopy. So this is one target, 3 epochs, geomorrhagi, and that again is in prep. And I'm still digging through that data set. But I just want to put it on your radar that hopefully that'll be coming out soon in the next few months. All right. Okay, so I want to tell you about first the HST sample that we have. So we got HST spectra for 5 young systems, and for each of these, they're ranging from 3 epochs to 8 epochs. And here, these broken lines correspond to the FUV part of the HST data, the NUV, the optical, and the near-infrared. And what I want to draw your attention to is the shaded parts, which correspond to the NUV data, where we're tracing the accretion onto these young stars. And if you look carefully and compare them, there should be one epoch that stands out to you as different from the rest. And that is this red spectrum here in geomorrhagi. So geomorrhagi did something very interesting for one of these epochs, so that's why we continue to follow up this one object. So I'll be focusing on geomorrhagi for the HST part of the presentation. So this is geomorrhagi, now focusing on the NUV, the optical, and the near-infrared. Here you see the epochs more clearly. We have 8 epochs of data. They're not evenly spaced, but the final 3 epochs are about a week apart. And you can see that the biggest change happens here in this red epoch, epoch 7. So to walk you through this, so epoch 6, so let's say that we're starting off here with epoch 6. So epoch 6 is in yellow down here. So lower NUV means lower accretion rate. About a week later, it pops up here to this red spectrum, so the highest accretion rate that we've measured for geomorrhagi. And then another week later, in epoch 8, in epoch 8, it comes back down. So we think that this is an example of a burster. So the YSO-VAR team has characterized as the burster class that I showed you in the Corot data set. This quick jump in accretion is compatible with being part of this burster class. And here, we're taking the last 3 epochs, 6, 7. 7 is where we saw the burst in accretion, and 8. And here I show modeling this data in detail to extract accretion rates. So first I want to point out, before I dig into the details of the figures, that in epoch 6, the accretion rate was 0.6 times 10 to the negative 8 solar masses per year. It then jumped up to 2 times 10 to the negative 8 solar masses per year, and then back down by about half to 1 times 10 to the negative 8 solar masses per year. And this is all within about one week each between each of the epochs. So here, breaking this down, I'll just focus, I'll focus on the middle panel here. The data are in black. The photosphere, or what we expect the photospheric emission to be, our template, is in blue. So all of this is excess emission. The gray bars here are masking out strong lines that we're just reproducing the continuum in our fits, not the lines themselves. And these different, and the red is a total model. And here we have 3 different colored lines. We have green down here, we have blue, and magenta. Now, I showed you before the simplistic 1-column model. Here we're using 3 of those columns to reproduce all of the emission that we see in the NUV. And those columns have different energy fluxes. So we have one with a low energy flux of 1 times 10 to the negative 10, 1 times 10 to the 10, one of 1 times 10 to the 11, and one of 1 times 10 to the 12. So that's our high energy column, and a low energy column, and a medium energy column. And we need all 3 to reproduce the emission that we see. And here, what's listed here, the little f, is the filling factor for each of these columns. So what fraction of the stellar surface is being covered by these accretion columns? So this is one of the unique things about having STIS and UV data, that we can start to parse out some of the properties of these accretion columns. What are their energy fluxes? How much of the stellar surface is being covered by the accretion column footprint? And this kind of work cannot be done from the ground because, as you can see here, we have a lot of energy that's being emitted shortward of 3,000 angstroms or so, which unfortunately we can't get from the ground or any other facility. Okay, so we see this big jump in the accretion of geomorrhagi in one of the epochs. And I just wanted to point out that this factor of 2 change in the accretion rate of G Maraghi, this has been seen in T-Tauri stars in larger surveys. So this is a plot of accretion rate versus mass of the star, and this is a scatter plot, and the error bars actually correspond to the range of accretion rates that were measured, and this is based on U-band photometry. So we can, from the ground, measure accretion rates. We just can't measure the properties of the accretion column. So G Maraghi's jump is not out of normal. What's interesting about it is that we were able to catch it, and you'll see in the next few slides in other wavelengths at the same time. And this shows how important it is to get large samples of accretion rates. And this is using U-band data, but of course the next generation of large surveys, TESS, LSST, they probably, so they're not going to be probing the U-band, so we have to come up with other ways of measuring the accretion rates with the data that's going to be available. And this is work that my student is doing now. So varying our accretion shock model and using it to generate what is the emission that we would see in the TESS filters. We can also do this for the LSST filters to see what kind of variability can we see at these longer wavelengths, and so that we can still back out something on accretion. So utilizing the data that we know will be coming in the future. And we're currently working with a couple of theorists, James Owen and Fred Adams, to do some simplistic simulations of how to pulse the accretion in these systems. So how do we represent a random turbulent accretion in order to reproduce, then when we have these light curves from TESS and LSST, to be able to back out what kind of physics is pulsing the mass that's changing the accretion rate in these systems. So that's work that we're still working on, that's in prep. Okay. So I just showed you some of the results of looking at the variable accretion rates. And what I went through quickly, but for the entire sample, it's always a little bit different. There's no epochs where they're exactly alike. So there's a lot of variability that we see in the accretion of these young systems. And one of the bonuses that we get with HST is that not only can we link the accretion properties in the NUV, we can then look at the FUV, because HST has FUV spectra. And there's one feature in the FUV that's called the H2 bump. So here it is. It's very bump-like. This is actually carbon. This is carbon 4. I think this is helium 2. But this is the H2 bump. So it's an unresolved H2 emission feature. And what's interesting about this is that it has 2 different proposed mechanisms. Oh, and this is a G Maraghi. So all of the epochs that we have. So you see that there's some variability there. And so the 2 mechanisms that have been proposed to trace, so the H2 feature is important because it's probing gas very close to the star. Close to where we expect that the material is being accreted onto the star. And there have been 2 mechanisms that have been proposed to explain this FUV feature. The first is due to X-ray radiation, and the second to Lyman alpha radiation. So the way that the X-ray comes into play is that it ionizes, so the high energy photons, the X-ray photons, ionize the inner disk, and some of the electrons can bump into H2 excited, and on the way down, it can give us this bump. Another way to do it is with Lyman alpha radiation, particularly Lyman alpha dissociation of H2O, with the idea being there that Lyman alpha dissociates H2O, H2 is in an excited state, and when it comes back down, it emits this feature. So both are very interesting because the first X-ray radiation, that would help us probe the ionization by X-ray in the inner disk, which is very difficult to measure. And the second would give us insight into dissociation of water. So we got, so for our sample where we had the HST spectra for all those objects, we also got coordinated X-ray data. And unfortunately, we don't see correlations with either the X-ray or the Lyman alpha. So here is the luminosity of that bump versus the X-ray luminosity, and there's no correlation. So we don't think it's due to X-ray ionization. And then this is a plot. So this is G Maraghi epoch 7, so where it was in its high accretion state, where we've subtracted out the lowest accretion state in order to see if there's a difference in the Lyman alpha lines. And the Lyman alpha lines are highlighted here in gray bars. and you see that there's no big emission. There's no big difference between the two. So we don't see evidence that Lyman alpha radiation is changing between the epochs. So that's what we were looking for when we did this coordinated study, and we didn't find it. But what we did find that is interesting, and there were hints of this before, is that the luminosity of the H2 bump correlates with the accretion luminosity, and it's pretty strong. And so, in most cases, maybe the simplest answer is the best, where there's more accretion, there's more mass in the inner disk, and that's why you see H2 emission. And we can't completely rule out that it's not due to X-ray or the Lyman alpha radiation field, but it does seem that the changes in the accretion, the surface density in the inner disk, would wash out any correlations that there would be between the two mechanisms. Okay, so that's the main result from looking at the accretion, the H2 feature in the FUV, accretion, and the X-ray. So we got this coordinated X-ray and accretion information. So we decided to look for correlations in other facets. So most of the X-ray emission from these young stars is thought to be generated by the corona, coronal emission. But there are some works where these young accreting stars have a soft X-ray excess. And there's some discussion as to whether the soft X-ray excess is coming from the accretion shock itself, or if it's coming from accretion-fed coronal loops. And this is just to show you that TW Hydra, which is the closest T-Tauri star, can be reproduced with a mix of coronal emission and accretion shock emission. So with our data, since it's coordinated, we can test this. So we found that the accretion rate does not appear to be directly correlated with the X-ray luminosity. So here we have accretion rate versus X-ray luminosity, accretion luminosity versus X-ray luminosity, and we don't see any correlations there. And also for GMRIGI, for this object, for those 3 epochs that I told you about, that I emphasized before, we got strictly simultaneous Chandra data with the HST data, and they are exactly alike. So there was a huge jump, a factor of 3 jump in the accretion rate in epoch 7, which is right here, but the X-ray, we see no correlation. So what we see is that we don't see evidence for an immediate correlation between the changes in accretion and any changes in the X-ray. Of course, one thing that you could say is that maybe a factor of 3 change in the accretion rate isn't enough to lead to changes in the X-ray emission that would be due to accretion. Or there's this other idea that was proposed that maybe it leads to heating, accretion-fed heating of the coronal loops. And the way that this would work is that you have the accretion shock, the emission travels, the radiation from the accretion shock, then you have some UV emission, you have veiling, which is measuring the heated photosphere, and then you get to heat the corona. So our observations could be indicating, so we didn't get, so this happens on the time scale of about a couple of hours, and unfortunately we didn't have X-ray data in between. So perhaps 2 hours, if we had Chandra data 2 hours after the accretion burst in GMRIGI, maybe we would have then seen an increase in the X-ray emission. So this is interesting to follow up with future work. All right, so we didn't see, so we saw a puzzling and interesting correlation with the X-ray. So maybe there aren't correlations, immediate correlations with the between the X-ray and the accretion rate, but we do see a correlation between the accretion columns and the X-ray luminosity. So this here, what we're doing here, so remember I told you that we're using 3 accretion columns to fit the excess emission, and they have different energies. So what we did is we took a weighted energy flux. So we weighted based on the filling factor that we said each of the accretion columns has. So here we have a weighted energy flux of the accretion column for the sample that we have X-ray data for, and we do see a positive correlation. So what could this be telling us? So this point up here is actually GMRIGI again, and this is in epoch 5, which is where we had SWIFT data. So we didn't have Chandra data for that epoch. So here's all the X-ray data that we have for GMRIGI. So here's the Chandra data that I showed you before, and here the less great data is the SWIFT data. But you see here that in EPIC 5, there was a big jump in the X-ray luminosity of Giamaraghi. And that's what's driving this correlation here. So it's highly unlikely that an increase in the energy flux of the accretion column is leading to this big jump in the hard X-ray emission. But, and this is actually very typical of these young stars that have flaring events, that they have this hard X-ray emission. But it's interesting, maybe having a flare on these young stars can then have some repercussions on the energy of the accretion column. So this is something that we're still working out and trying to figure out. Why do we see this correlation between the X-ray emission and the energy flux of the columns? It doesn't seem to be linked to accretion, but maybe flares in some way affect the accretion onto the young stars. All right, so I told you about the accretion variability in the NUV, correlations or lack of correlations with the X-ray. Now I want to move on to where we actually see some strong correlations, which is between the NUV and the infrared. So here is Giamaraghi again, our favorite object. This is epochs 1 to 3. So here, just to point this out to you, so our HST data is here. So we have FUV, NUV optical, and a little bit of near-infrared. But the near-infrared data here is coming from SPECS. So ground-based infrared spectra from about 1 to 5 microns. And what we see here is that in this third epoch, epoch 3, the NUV emission is down, so the accretion rate is down. But also, if you look closely here, the red spectrum is lower than the other ones. So also the near-infrared emission is down at the same time, and we see this correlation. And just to remind you, the NUV, again, is coming from accretion, and this near-infrared excess is actually coming from some optically thin dust within the disk. So this Giamaraghi is a disk, and I'll revisit this later again, that has a large hole in the disk with a radius of about 20 AU or so, and it does have some near-infrared emission, as you see here, that we think is due to submicron-sized dust very close to the star. So we see a correlation between the accretion onto the star and the amount of dust in the inner disk. And we followed this up with simultaneous data between HST and Spitzer for epochs 4 to 8 of Giamaraghi. So these are Spitzer IRAC data. For the first two, the first channel is the triangles, and the second channel is the circles. And what you see is that there's this big bump here. And this is epoch 7, where we saw the big jump in the accretion. So before, in our 2015 paper, and here with our follow-up observations, it seems that there is a robust connection between accretion onto the star and the amount of material that you have in the innermost disk, the dust. Now, what does this mean? So we see this correlation, but it's not an expected correlation. And that's because the magnetospheric truncation radius, where material is being lifted off the disk and onto the star, we think that's at about 0.04 AU. And in Giamaraghi, if you run the numbers, the dust destruction radius, whereby no more dust can go in, it sublimates, is at about 0.08 AU. So it seems like a small difference, but this is actually a very big difference, several days on the viscous timescale. So why is there a correlation between the gas and the dust? So one idea is that maybe both the dust and the gas are at the co-rotation radius. So in order for accretion to occur, you have to be within co-rotation. So co-rotation is where the velocity in the disk matches the rotational period of the star, and you need to be within this because you want your gravitational force to overcome the centripetal force and not be flung out from the system. So what we think this is telling us is that there's actually dust that gets the co-rotation radius. And if we push our opacities to much larger grains, we can actually get the dust to 0.07 AU in the system. So what this could be telling us is that before we have this view where the gas is being accreted from a gas pure disk and the dust is out here, but maybe it's actually much more complicated than that. And there's actually dust and gas that's being accreted onto the star, at least at these points before it gets sublimated when it gets much closer. And our study isn't the only one that finds this. YSOVAR also found some examples of this with that Dipper star category that I pointed out before. So these dips in these particular objects correspond to the rotation period of the star. And one idea that they propose is basically that the dust is also located at the co-rotation radius or within, and is actually being accreted, lifted off of the disk along with the gas of the star. And they didn't have, for these objects, they didn't have simultaneous indicators of the accretion rate. So our work supports theirs. We have simultaneous dust and gas. So some revisions need to be made to our picture of magnetospheric accretion in these young stars. Okay. And just to emphasize the point that what we are seeing from these coordinated NUV and infrared studies is that we're probing the point in the disk where mass is being accreted onto the star. So of course, this is much more complicated, and we're not going to get to this point where we can understand exactly how things are being lifted off the disk and onto the star, but we're making some steps in the right direction. And the idea could be that we have some inhomogeneities in the inner disk. How do you get those inhomogeneities? That's for theorists to figure out, but it's not too hard. You have turbulence from viscosity, maybe you have planets that are mixing things up in the inner disk, but somehow you get some inhomogeneities in the inner disk, and that could lead to either more or less mass being accreted onto the star. And that's what we're seeing with the near-infrared and the NUV. Okay, so that's what we've learned from multi-wavelength, the coordinated simultaneous multi-wavelength studies that my group has done recently. Now, what is left to learn in the field? So a lot of questions come up. So one problem is there's a giant hole in the center of Geomorrhagi, and it's accreting very vigorously, and the accretion rate is changing with time. So a postdoc in my group, Enrique Macias, he did this work on Geomorrhagi, where he took some ALMA data, and we know that ALMA has a large cavity. This was first identified with the SMA. And ALMA this is just to show the ALMA data that he used. So it's not obvious from these images, but if you look at the visibilities, you can actually tease out that you have a large cavity in the disk and these two rings, or two gaps, in the outer disk. So you have a large cavity of about 20 AU radius, and then you have these other gaps in the disk at 40 AU and 80 AU. So not only, so how is accretion traveling through these large gaps so how's the gas traveling through these large gaps in the disk of Geomorrhagi? So that's a big question. And it's not unique. It's a question we're going to have to answer and really confront in the near future, because this is results from the large program led by Sean Andrews here. 20 disks, and most of them have gaps. And to the best of my knowledge, the vast majority of these are accreting. So it seems to be common. We have gaps in the dust structure of disks, but gas accretion still happens onto these stars. And here are just some examples. So you can argue, well, the gaps are smaller, so maybe it's easier for gas to go across the gaps. But just to remind you, we do have many, many disks that have large cavities, 40, 50, 60 AU in radius. And this is work with the SMA. So we have these huge cavities in disks. We have to figure this problem out. Now, you would think that ALMA would help us figure this out, but it's actually led to more questions. So here's an example of two disks where the broken line corresponds to the size of the dust cavity, and the red is tracing 13 CO in the system. So you can see that the gas does go through, but then it drops significantly close to the star, which is where you want your gas to be in order to accrete onto the star. So many more questions raised by looking at the ALMA data. One idea is that maybe there are supersonic streamers in the inner disk that funnel the accretion onto these stars. And okay, so we have the one problem that how do we get gas to accrete past these gaps in the disk? Another issue is that observations of turbulence in these disks is coming to the consensus that the viscosity in these disks is very low. And if you have accretion, that means your viscosity is high. So there seems to be this tension between high alpha from accretion, low alpha when you look at observations of disks. And here's just an example of how, so this is a very hard observation to make using CO and ALMA. On the left are the simulations where each of these lines corresponds to a different amount of viscosity in the disk, different amount of turbulence. And the idea is that if you measure the difference here the difference between the peak and the trough in these line profiles, you can put constraints on the alpha parameter in these disks. And here's an example of how you do it with observations. This is work coming out of Meredith Hughes's group at Wesleyan. So the data are in black. The broken red line is the simulation with high alpha, high viscosity, turbulence, and then the broken blue line is low, the low alpha case. And you can see it better when they normalize to the peak of the line, because what you want to measure is the difference between the peak and the bottom here. You can see that the best fit is provided by the blue, which is low alpha. And I think for this object, they measure alpha at point, I think it's 0.007, so relatively low. So if we look at just that, then it would imply that there's low turbulence in these disks. But there's also some recent work also coming out from the D-Sharp program that maybe the viscosity is radially variable in these disks. And there's no reason why alpha should be the same throughout the disk. So here are the observations of AS209. Here you see the radial profiles. Here are simulations with a low viscosity, alpha 10 to the -5. And here are disks with, where you vary the viscosity radially in the disk. And you don't see a huge difference here in the radial profiles, but you can see here with the spatial brightness distribution that you do a better job of reproducing the observations when you let alpha vary and increase as you get into the outer disk. And the idea here is that in the outer disk, you can actually have the ionization of the outer disk. The cosmic rays can penetrate down into the outer disk, and that will increase the ionization and the alpha. So maybe there's hope for reconciling this. And then another idea that may be able to reconcile this seeming tension between the high alpha inferred from accretion and the low alpha inferred from the ALMA observations is the idea of dead zones and active layers. So the idea here is that the X-rays don't ionize down to the midplane of the disk, so you have a dead zone where you could have low alpha. But then the X-rays can ionize the uppermost atmosphere of the disk and the outer disk, and their idea is also that accretion can happen just via the upper layers of the disk, so just via these active layers in the disk. So maybe this can resolve the tension, because when we're measuring accretion rates, that's measuring the rate of the surface density changing throughout the upper layers of the disk, and then the ALMA observations are probing more perhaps the dead zone, and in some cases in the outer disk. So maybe this is how we can reconcile all these things. Still doesn't explain how you get the gas past those big gaps, though, so that's still an active area of research. Okay, so we can extrapolate some things. So why study accretion in Centauri stars? So one interesting aspect of this is that maybe by better understanding accretion in circumstellar disks, we can start to move towards understanding circumplanetary disk accretion. And here's the most robust detection we have to date of a protoplanet, and this is in PDS-70. This is an infrared continuum image. Here on the right, and you can see more clearly here, is an H-alpha image. And if you remember, H-alpha we think comes from the accretion process. So this is evidence that there is accretion occurring onto these young planets as they're forming. And then the question is the magnetic field of the planet strong enough so that this is basically a smaller version of circumstellar accretion, like we see in the Centauri stars? Or is it happening via boundary layers? And then, of course, if we want to better understand how we can apply what we've learned about circumstellar accretion disks to circumplanetary accretion disks, we need to detect these circumplanetary disks first. And this is just an artist's conception of you have a planet with a strong magnetic field, and you have a little accretion disk around it. These disks, so here I don't want to go too much into detail. I just want to highlight that most of the emission that you see in these circumplanetary disk models with different accretion rates occurs in the infrared wavelengths. That's where you're going to see most of the emission from these disks. However, they're brightest in the infrared, but they should be able to be detected in the millimeter, perhaps. And here's a simulation of what a circumplanetary disk would look like in the millimeter. These are very tough observations, though, to make. You have to sit on the source for a long time. And also, it's expected that, I didn't get into the physics of dust radial drift in disks, but maybe circumplanetary disks have even smaller disks, very, very narrow disks. And so it'd be much harder to detect it with detect them with ALMA. So for now, ALMA is our best hope for detecting these circumplanetary disks, but it is a hard observation to make. Okay, and then just looking forward to the future, the next class of 30-meter telescopes, we're going to be detecting protoplanets left and right and their circumplanetary disks. And also what's very important about these large telescopes is that we're going to be able to start chemically mapping the innermost disk and being able, so ALMA is going to give us a lot of information down to about a few AU or so, but still the inner AU, how the gas is going to be hard to parse out spatially. So so 30-meter class telescopes are going to be wonderful for this and telling us how the gas is spatially located close to the star. All right, so to wrap up, we've made a lot of progress in understanding variability in these young systems and also protoplanetary disks in general. I think that with multi-wavelength work, where we're probing the star, accretion onto the star, radiation fields from the star and the X-ray, and also near-infrared emission, where we're getting at the disk, and also the millimeter, we can start to get a clearer view of snapshots of these disks in time because they're not static objects. And so it's important for current and future facilities to help us facilitate this kind of multi-wavelength work. And with that, thank you very much.
Thank you, Catherine. Any questions?
How do you get the spectrum of the photosphere? Is that just a calculation, or can you actually observe that?
Yes. So for our objects, we can get, they've all been spectral typed in like the visible. So we do see, so there's some accretion, shock emission in the visible, but mostly there you see photosphere. So you can spectral type them. Is that your question?
Well, so the spectrum you have of the photosphere is the spectrum that it would have if it were that kind of star.
So those blue spectra I was showing, saying that they're the template, that's a weak T-Tauri star. So a T-Tauri star that's not accreting, it doesn't have a disk around it that we know of the same spectral type.
Yeah, Jane?
So you mentioned the tension between the accretion rates and the apparent disk viscosities. Can your data place any constraints on whether MHD wings are acting in these disks?
Oh, yeah, that's a good question. To get at the wind emission, there's been some recent work looking at the oxygen lines in the visible with high-resolution spectrographs. So our data, is best for looking at the accretion, not the wind. But there is some work looking at high-resolution optical data of the oxygen forbidden lines, where they say that they see some of the broadening can be due to disk wind.
Yeah, early in your talk, you showed this very nice, very simple explanation of the difference in the profile around 10 microns that is attributed to an inner wall and then a 40 AU gap. And it's very believable, but it seems like one way to actually prove that that's the explanation is 40 AU is about 5.5 hours light time. That if you monitored a star, that you should see a lag between the distortion in the nearer infrared part of the line profile and the far infrared side of that profile by about that light travel time.
No,
that would prove it.
Yeah, no, that's a great idea. And we got that data in the last cycle of Spitzer. So we weren't able to follow it up. And we can't follow it up until JWST.
Yeah, JWST is the obvious.
No, that's a great idea.
Joey?
So you mentioned the circumplanetary disks, and obviously that's really exciting. So we've had a few of these candidates, and I think none of them are really panned out. So you mentioned that the disks around these circumplanetary objects can be very small, and the sizes that we're estimating for some of these candidates are 2, 3, 4 AU, like Saturn, like ring, like size, like distribution, but much bigger. So why do you expect the disk to be so small, and why do you think there's kind of contrast here?
Yeah, so I was talking specifically there about millimeter. So the millimeter. So they could be much bigger in the small grain distribution and the gas distribution. So what we see in circumstellar disks is that when we look at the gas distribution, the gas goes out to a few 100 AU, 200 or 300 AU. But when you look at the dust, it's very compact. So it could be scales of 10 AU. And the longer the wavelength you look at, the more compact the disk gets. And that's due to the radial drift of dust grains. So the larger the dust grain, the more efficient the radial drift into the inner disk. And the idea is, so in the millimeter, we're seeing larger disk grains, and here we have very, very small disks to begin with. And if this radial drift process is happening in these disks, maybe we get these very, very thin rings that we just can't see in the millimeter. So we'll see, right? People are looking for these circumplanetary disks, and the question is, why haven't we seen them yet? Maybe it's this, but stay tuned. We just need to sit on them longer and figure it out.
So I'm intrigued by your flare connection with the accretion. It's like an accretion power.
Energy flux.
Can you say something more about what were the properties of this flare? Do you see any connection, like a time-connected event, or if this was a simultaneous observation?
Yeah. So where we saw the X-ray flare in GMRID, that was EPIC 5. That was SWIFT data. And SWIFT is a TOO instrument, so it's very difficult to get strictly simultaneous data. So we have like half of the data set was simultaneous, and the other half was taken within like 12 hours.
I'm sorry to interrupt. Is it after or before?
I have to double check. I think it was before, but I have it here if you're really curious. So so that was the SWIFT data. And when we look at the accretion, there's no significant changes in the accretion rate itself. The only thing that really changes is that you need higher energy columns to fit the shape of the NUV spectrum. So, and then most flares in these young stars emit in the hard X-ray emission. And we don't think that accretion generates hard X-ray emission. So I don't think there's a connection between the accretion process and hard X-ray emission, but I'm wondering, could the high energy of the flare somehow radiate the accretion columns and somehow impart more energy to them?
So what I'm thinking is, like, I don't know, but maybe you can look this up. There are several or some examples of, because flares usually don't come alone, at least when we observe in the sun, it generates coronal mass ejections with it.
Yeah.
And sometimes these coronal mass ejections, they fail to go away. So all that material is channeled back to the star. So maybe you're seeing some sort of a massive, failed CME eruption that goes back into the star and then is modifying your accretion profile.
Well, I'll look at that more carefully. What I can tell you is that our HST data was from the FUV to the near infrared, and we didn't see any big changes at any wavelengths. So that's the best I can tell you to constrain that.
All right, I have a question for you. So you mentioned the tension between the accretion and the transition disk holes. And okay, the CO is leaking in, but there's still a hole in the CO. And my question is that really a problem? Or could the CO just be destroyed inside of a certain radius and the H2 is gone all the way in?
So the CO...
could you just be destroying the CO? Could it just be like an abundance effect?
So the people who published that have a pretty good grasp on chemistry, so I think they would have looked into it. Okay. But I don't want to, Karen's laughing. So I think they thought this through, and it's not due to CO photodissociation. But that is a common question that I get.
But could it be an excitation? That as you get closer to the star, the emission in the CO transition you're observing gets weaker in favor of higher J transitions of CO.
Okay, that's interesting. I'll think about it. I don't know if you want to weigh in or...
I actually don't remember what they took into account in that paper. I wouldn't rule out any of these two ideas completely.
Okay.
I mean, I think it's a rather complex thing. We don't really know how the shielding of how well things were shielded. So.
Okay.
That's good then.
Yeah. So there's some wiggle room there. So maybe it's not all hope is lost.
Exactly. All right. Any more questions for Catherine? All right. Otherwise, let's thank Catherine.
Oh,